Welcome to the April 2024 Research Lightning Talks hosted by the Center for Research and Creative Activity. Thank you to everyone for attending, and thank you to all who have contributed to our past events as well. We have 6 presenters today who will be discussing this month's topic, AI and research. I will introduce each speaker before their presentation, and then each presentation will be followed by 1 to 2 questions from the audience. After each presenter has finished speaking, please feel free to unmute yourselves and ask your questions. After all 6 presenters have finished, we will then open up breakout rooms so that each of you can go visit with a presenter of your choice to discuss any insights or questions that you might have. And you'll be able to go back and forth between different rooms during that time. That way, if you have lots of questions for lots of people, you'll have the ability to try to go hit up everybody. But with that, I will go ahead and begin with our first speaker, Dr. Andy Hung. Dr. Andy Hung, who is a faculty member in the Department of Educational Technology, is in his 17th year at Boise State University. He earned his doctoral degree in educational technology with a minor in information systems and quantitative science from Texas Tech University. His research focuses on learning analytics and machine learning in education, resulting in over 60 publications and the development of new algorithms tailored to educational data and contexts. Today, he'll be talking to us about empowering research, collaborative multi-agent AI for data analysis and interpretation. Dr. Hung, the floor is yours.
Yeah, thanks for having me, Catherine. So the study is entitled Empowering Research Collaborative Multi-Agent AI for Data Analysis and Interpretation. And what is the multi-agent AI system? The system contains a team of multiple AI entities to assign, collaborate on, and monitor tasks in order to complete a more complex task. Because modern analytic methods or algorithms has posed higher entrance barriers for researchers to utilize these analytical methods and understand the results correctly, the purpose of this study aims to construct a multi-agent AI system which can complete social network analysis and interpret results automatically. The concept of a multi-agent tool actually is not new. However, due to the recent progress in large language models, the potential of multi-agent tools has attracted a lot of attention. The most famous frameworks available at this point are Alderden and the Crew AI. And these frameworks allow you to construct a team with multiple AI entities. The entities can be large language model, other machine learning algorithms, or even other office tools. And due to the time constraints, I cannot go too detailed, but you are welcome to ask me if you after this presentation. Yeah, I created the following agents for the tasks of data analysis and the result interpretation. So the user proxy is a liaison of the user. It is the leader of the team and in charge of monitoring the collaboration process, executing the code generated by the coder, and checking the results. The coder is the programmer in the team. It is in charge of generating codes based on the user's needs. And the examiner is another checking point. Its role is to ensure that the user proxy will execute the code and check the results. And we also have the SNA expert. It's a domain expert in social network analysis. It contributes domain knowledge in SNA during the group discussion process. And finally, the chat manager is in charge of coordinating the group discussion process. And you can see on the slide contains a screenshot of the collaboration process in Jupyter Notebook. So basically, this agent collaborate with each other through group discussions. For example, the coder will generate a Python code based on the task goals. And the user proxy will execute the Python code and to examine whether the results align with the original task goals. If the results fail to align with the goals or the execution fails, then the user proxy will return the job or error messages back to the coder and the coder will revise the code and repeat the process. And the dataset used in this experiment is an open dataset of online course discussions extracted from Coursera with more than 10,000 students. And the study consists of 6 parts and is still ongoing. So here are some initial results of 20 rounds in the tasks of data exploration. And we compare the multi-agent AI system with the single agent OpenAI's code interpreter. And the results show that the multi-agent AI system slightly outperform the OpenAI's open code interpreter in task understanding and the result correctness. Yeah. Thank you.
Awesome. Thank you so much, Dr. Hung. We appreciate you being here and telling us all about this. Audience, you now have about 3 minutes to be able to ask any questions that you might have.
Hi, can everybody hear me okay?
Yes.
Hi, thank you. Great talk, Andy. I really appreciate you being with us here today. I have a question for you in regards to, based on your experience, what are the major limits or challenges with multi-agent AI?
Because the limit of the token numbers, and also maybe just because right now I'm using OpenAI's API, so it and the results can be heavily influenced by the stability of the API codes, and also the token, because these agents actually they collaborate with each other through group discussions. So actually, it will consume more tokens than the user interact with the OpenAI's agent independently. Yeah, so that's something I will consider as a constraints or limits at this point. Yeah.
Awesome, thank you.
Mm-hmm.
I have a second question if nobody else wants to jump in, and it's, are you conducting any other studies using this framework?
Yes, because we have the EdTech has a EDD program, and actually student encountered lots of difficulty in the proposal development. And we try to create another group of agents which allow students to interact with the team and to get the constructive feedback from these agents and to improve their proposal quality before submitting to the committee members.
Thank you.
Mm-hmm. Thank you.
So I just have a quick question, Dr. Hung. How
Yes.
do your preliminary results using this method differ, or how similar they might be to just the more traditional social network analysis, in terms of interpretation and, the results that you get?
Yeah, we are still working on the interpretation, but we really focus on whether the tool can generate like a more in-depth insights on the result interpretation rather than just generating like a simple indicators from the data only. Yeah, but we're still working on that. We can see actually sometimes the agents can generate really insights and align with the data set, the property of the data sets, like for educational purposes, from the aspect of the educational purposes, but not every time, just sometimes. Yeah, so we are still try to improve and try to improve the reward function. So in order to get the agents to become smarter and to be more domain specific purposes. Yeah.
Thank you very much. Very exciting.
Thank you.
Awesome. Thank you again, Dr. Hung. We're going to have to go ahead and cut questions off, but please, if you have questions, write them down and then you'll have time to ask them in the breakout rooms. So we'll go ahead and move on to our next speaker, Dr. Casey Kennington.
Thank you. Oh, sorry, you're going to introduce me.
No worries. Yeah. So Dr. Casey Kennington is an associate professor in the Department of Computer Science and is an affiliate faculty in the Department of Linguistics. He obtained his PhD in linguistics from Bielefeld University in Germany. His research involves computational semantics, or how computers learn, represent, and use linguistic meaning as they interact. He's worked on language models and robots to further his research. He's going to talk to us today on computational meaning. Go ahead and take it away, Casey.
Thank you again. It's great to be here. Can computers think? Does a chatbot understand me when I type a prompt? In order to answer these questions, I think it is important to ask yourself, what do you mean by think and understand? Both are complex processes that require knowledge of English grammar and, more importantly, the meaning of language itself. Meaning of, or semantics, is a field of study that touches neuroscience, psychology, cognition, child development, linguistics, and computer science. How do words come to mean what they do, and how can we convey that meaning into computers? To explore semantics a bit further, I'd like to introduce you to 3 ideas of meaning of language that can be processed by a computational model. The first is formal. The first builders of computers dreamed of using them not just for powerful computations, but to make them into machines that can think. Computers are built on logical processing of ones and zeros. Logic is great for many complex linguistic phenomena like quantification, inference, and reasoning, but brittle for other linguistic phenomena and very difficult to map from words that we say and write to logical representations, useful but limited. The second is distributional. Besides logic, computers operate very efficiently on numbers, but how can we represent the meaning of words in language as numbers? Well, if we take a big corpus of text, for example, you can download Wikipedia right now, then you can find the most common 1,000 words that are used. Then we can compare all other words to how often they show up around those common 1,000 words. For example, we can take the word dog and find every time dog shows up in Wikipedia, look at the 3 words before and after each use of dog, and count the times when the most common 1,000 words are there. This results in a list of numbers, or a vector, for the word dog, and in a different but similar vector for the word cat, and a very different vector for the word car. In fact, if we treat these vectors as points in n-dimensional space, we find that words with similar meanings cluster together. Animal words are over here, while vehicle words are over there. Instead of just counting, we can have a computational model learn vectors by giving it examples of text and having it guess missing words, then using a more complex model that can work with these vectors by shifting them around to understand the difference between words like apple the fruit versus apple the company. What's even better is that these vector representations are perfect for general purpose machine learning classifiers like deep learning. Hook them up in a certain way, and we get the transformer architecture, which is what the T stands for in ChatGPT. The third is grounded. Have you ever thought about the meaning of the word red? Red, of course, is a color, but so is green and blue. Yet they are different from each other. Red doesn't really have a dictionary definition. Rather, it's something visual, something that we see in the world. The meaning of many words is tied to our physical interactions, anything you can touch, see, or otherwise physically interact with. Look around you and you can pick any object that you see at random, and you can probably produce a word or description of that object so you can talk about it with someone else. One of the problems with representing linguistic meaning using logic or vectors trained on text is that the meaning of many of these physically grounded concrete words is missing. Newer language models bring the visual world into the vector world, but only as a third-party observer, not as a first-person experience. Every single person who has ever lived and learned a language learned their first language by being an active, physically embedded and participating in the world around them. Much of the language of our first words are grounded into our sensory motor experience. More abstract ideas, for example, democracy, are learned later after there is a base vocabulary of more concrete concepts to build on. With this overview of the 3 approaches to computational semantics, we again ask, can computers think? Does a chatbot truly understand? Here's a thought experiment. If I have never been to the Grand Canyon, but have only read about it and seen pictures, can I say that I truly understand the Grand Canyon when everyone who has seen it in person emphasizes that seeing it in person is an experience that is vastly different from just looking at photos? If that's true, then computers can think and understand, but only abstractly. ChatGPT has probably been exposed to more text than any other human who has ever lived, but even if ChatGPT could read about everything, its understanding is only an abstract approximation, useful to be certain, but not a rich comprehension of meaning. Clayton, a PhD student in my research group, is working towards bringing the sensory motor world to language models. Catherine, a master's student, is working towards building native curiosity in robots so they can learn categories of objects that form the basis of what language is later grounded into. Drew, Beth, and Gerardo are working on bringing emotion into language models via robot behaviors. This work will help models of language better understand the meaning of words that we use, which will enable people to more naturally interact with technology. Thank you.
Thank you so much, Casey. We appreciate that. Audience, you now have about 3 minutes to ask any questions that you might have. I have a question in the event that nobody else does, but I was curious, you talk about the teaching of language kind of in a way, where humans learn it and then machines learn it. Do you see any similarities in that process where, humans are learning their language and then robots are learning the language, and like there's kind of overlap with that of like similar experiences?
Well, not really. The way ChatGPT learns is purely from playing a game of guess the word with lots of text. It is given trillions of examples, but that's it. The first thing I asked ChatGPT when I first used it was, have you ever seen an apple? And it said, no, I've never seen an apple. I've never seen anything. And it's not that you have to see things to understand them, but the word kick is grounded into our sensory motor experience of having kicked things, not just watching people or reading about someone else kicking things. And that extends to thousands of words that we speak. So there's a lot you can read about the meaning of words, and you can get a lot of information from just text, but it's not as rich as what humans have.
Awesome, thank you.
I have one question.
Sure.
Is there any way or any indicators that can be used to confirm the model has inference capability?
Inference is, there are benchmarks and data sets for inference evaluation in the natural language processing field. And so if you want to know more about that, you can send me an email. But yeah, there's stuff out there, some benchmarks for it. Mm-hmm.
So can I ask a follow-up question? So
it looks like Ezra has a question.
Oh, sorry.
I'm just very curious. Is this like related? I sometimes wonder if there's a way for AI models, especially chat models, to sort of understand connotation, right? Like the difference between if someone says house versus home is a very common one.
Yeah. I would argue that the only thing they're understanding at the moment is connotation, not denotation, because there's no exposure to denotation. But given the way the transformer models work, like the large language models like ChatGPT work, they're designed to differentiate between valence, like positive and negative valence in how you say stuff. But the slight differences between like a house and a home, it can get to a point where it's a vector where house is over here and home's over here, and it's a matter of where the vectors are, and if it can, as long as it's been exposed to them in the text, it can get the nuances. But that's not the case with every concept or every connotation.
Interesting. Thank you.
I have a question. You mentioned how children learn their first language by participating in the world around them.
Right.
Do you think that embodiment is necessary for language learning?
I do, personally. And when you say language learning, you can point to you can point to ChatGPT and say, is it really necessary? These things are doing pretty well without embodiment. But there are very important nuances to the meaning of many words that has to do with our sensory motor experience. For example, a lot of verbs, like I mentioned, kick, you could read about kick, but experiencing kick or throw or eat or swallow or something like that, plus the fact that we have base needs like survival, we need food, we need shelter, those play into our motivations and goals that we have. And that of course affects the kind of how we use language and what we do day to day and what we talk about and how we talk about it. And I have quite a bit of I think empirical backing for that, for the research that I do, but also a lot of there's a whole research field of cognitive embodiment or embodied cognition that I can point anyone to if they're interested. But there are, of course, many people who don't think that it's required. Text is fine.
Thank you.
Awesome. Thank you, Dr. Kennington. We'll go ahead and stop the questions here. But again, write them down if you have more and visit Dr. Kennington's breakout room later. Awesome. We're going to go ahead and move on to our next speaker, Dr. Jenny Alderden. Dr. Jenny Alderden is an associate professor in the School of Nursing. Her research focuses on preventing pressure injuries in critical care patients. Drawing on her extensive experience, including her role as a helicopter nurse during the Iraq War, she understands the critical importance of data-driven care. Alderden's research now concentrates on creating explainable artificial intelligence models to enhance outcomes in critical care environments. She'll be talking to us today about explainable artificial intelligence for pressure injury risk prediction. Dr. Alderden, the floor is yours.
Hi, thank you so much for having me. The motivation for my work with artificial intelligence stems from my experiences being a critical care nurse. In 2007, I was a critical care nurse during the Iraq War troop surge, and most of what I did was fly in helicopters with badly injured sailors, airmen, and Marines. In 2009, I got out of the military and I went to the University of Washington and started working on my master's degree there. And while I was there, I went to a VA in Seattle, and I walked into a patient's room, and the patient turned out to be this young Marine that had flown in my helicopter. But the reason he was still stuck at the VA instead of home with his family was because he developed a pressure injury. Pressure injuries, which are also known as bed sores, are preventable, but common skin injuries in critical care patients. We know that if we put in the right preventive interventions for the right patient at the right time, we can prevent pressure injuries. However, we don't always know which interventions to give to which patient. We do pressure injury risk assessment in the ICU every 12 hours right now, currently all over the United States, but we use a tool called the Braden scale. And the Braden scale was developed in 1987. It's a pencil and paper tool. The Braden scale is highly sensitive. That means that it can identify all patients as high risk. The problem is that it identifies every ICU patient as high risk. So it's not at all specific. It doesn't let nurses differentiate or determine what a certain patient needs based on their individualized risk. So what our team is trying to do is develop a tool to accurately assess pressure injury risk and enhance clinical decision-making in a way that will allow nurses to differentiate among ICU patients based on risk. We see AI as a solution to this because AI can be used to enhance, but not replace, nurses' clinical decision-making. We can use artificial intelligence models based on pre-existing EHR data to improve the accuracy and the timing of pressure injury risk assessment, and we can use it as a support tool. We can use it to complement nurses' clinical insights. So what our study did, and I'd like to thank our funder, the American Association of Critical Care Nurses, we used a comprehensive ICU EHR dataset called MIMIC, and the wonderful computing team here at Boise State gave me a great deal of help getting the data ready to use for our analysis. We ended up employing a superlearner ensemble model. It's a type of machine learning, and the person who really pioneered this is Dr. Mark Vanderlaan at UC Berkeley. And I was very fortunate that he was willing to be a co-author on the paper. He helped our team develop our ensemble model. And our model is focused on early detection of pressure injury risk. And the reason we focused on early detection when a patient is new to the ICU is so that we can enable timely interventions. However, our model, our ensemble superlearner, is still a black box. Study after study has shown that it's very difficult to implement artificial intelligence in the ICU or in any place that you have nurses and physicians because they don't understand how the model is making its decision, either globally, how that model works, or individually at that individual patient level. So what we developed was a explainer dashboard. We created a synthetic data set based on our real data set so that we can share the dashboard without violating patient privacy. And you see a picture of our prototype dashboard here. The explainable dashboard makes the AI predictions understandable and actionable, both at the global and the local level. Because again, our goal is to support, not to supplant nursing judgment, and we want to know if nurses trust our model. The results and the impact, our model greatly outperforms the Braden scale right now. The AUC is about 0.79 compared to 0.6 for the Braden scale. The dashboard provides critical insights for tailored interventions, also based on some modifiable risk factors. If it's identified, it can suggest something nurses can do. And we hope it will enhance patient care by providing better preventive strategies. So for next steps, one of the things that we are exploring doing is enhancing the model by including input from nurses, input from users, and finding out the things that they see wrong, places we can make adjustments. Again, we wanted to thank our funder. We have some early good feedback. We submitted our model to the Society for Advancement of Wound Care, and we won the Research Abstract Award. And then at the American Association of Critical Care Nurses National Teaching Institute, which is their big 50,000 person conference, we just won the Best Abstract Award. And we just yesterday found out that this paper was accepted, the one that presents the dashboard and the model, in the flagship Critical Care Nursing Journal. And then finally, our team was invited to participate in international guidelines with a focus on the role of AI in pressure injury prevention and wound care. So our work is ongoing. This is a prototype model. It's very imperfect, actually, but we're excited by the idea and hopefully more of this in healthcare.
Awesome. Thank you, Dr. Alderden, and congratulations for all of those amazing accolades. That's amazing. Audience, you now have some time to be able to ask questions.
Hi, my name is Michelle. I'm sitting on my coworker Roxanne's screen though. This was so interesting. Thank you so much for sharing. I had a quick question just about what are the main factors that you think cause distrust on the nurses who use this?
So one of the things that happens in a lot of modeling in the hospital setting is that people who are not very familiar with the data generation process take the data and then they say the data speaks for itself. And the reality is data that is generated by nurses sometimes means very different things to the nurses. For example, missing data are present a lot of the time in the data sets that we work with, but a lot of teams don't really understand that missing data in healthcare data are always missing for a reason. So for example, we have lots of missing data in something called an arterial blood gas, but that's because it's a pretty invasive test and only patients who are having trouble breathing are really people we're going to submit to that test because it really hurts. And so, so one of the things that I think will enhance trust is helping nurses see we really do understand what this data means and also what it doesn't mean. And also, it's too much for this topic, but we do have real problems with underrepresentation in our data too. Some patient types, some groups, people who don't access healthcare a lot, are not always well represented in our training data, and that is a problem that I'm grappling with.
I have a quick question. Hopefully it's quick. You mentioned the model is an ensemble model, but it's that could be a lot of different things. Can you say a little bit more about what is happening here? Because a lot of machine learning models are notoriously opaque and you can't really interpret them, but this is showing like, here's what's more important, what's not important. Can you say a little bit more about those?
Yeah, so in order to make an explainable dashboard out of the ensemble model, we had to choose a tree-based model within it. So we made the random forest model within the ensemble model, the interpretable thing here. And again, this one is also synthetic data. So the model that we share with our QR code for people to play with is it is based on all the trees within these. So there's a random forest, I forget what else. It's based on only the tree-based models within our ensemble superlearner. And it's based on not the real data set, but a synthetic data set.
Thank you. That makes sense.
I have a quick question as well. So when you obtained your first random forest model and to interpret the model with the global importance, did you see any like a relationship or the importance doesn't align with your domain knowledge or practical experience?
Yes, and in fact, we had to make a big adjustment, Dr. Hung. One of the things that I saw, a mistake that I made is sometimes our model importance in our very first set variables that should be very important were not near the top. And what I realized was that patient censoring was a big problem. So patients who are very high risk for pressure injury also often die. And until I adjusted the model to pay attention to the patients who die and not to pull them out as zeros, as not getting a pressure injury, I had a very poor performing model, and I didn't quite understand why until I met with some domain experts, critical care nurses, and we talked through it. Because yes, looking at which variables were important, our first iterations of the model did not align with our domain knowledge.
Thank you.
Awesome. Thank you so much, Dr. Alderden. Appreciate you coming in and telling us about this. This is amazing. We'll go ahead and move on to our next speaker, Dr. Brian Stone. Dr. Brian Stone received his PhD in cognitive psychology and his master's in neuroscience and behavior from the University of Georgia. And before that, a BA in philosophy of mind from Washington State University. He has studied various aspects of cognition in adults, children, animals, and machines. His interests include perception, decision-making, tool use, human factors, and accessible design and learning. He teaches various courses in experimental psychology here at Boise State University and has been researching the way students use and think about LLMs and other AI. He's going to talk to us today about fear and confusion in LLM land, student uncertainty around AI. Dr. Stone, the floor is yours.
Awesome. Thank you. Hello. So as Catherine said, my name is Brian Stone from the Department of Psychological Science. I've been researching student usage of, perceptions of, beliefs around, and worries about AI. At this point, I've surveyed around 800 of our students, and the data here today will come from a chunk of that, but I'm also running a bunch of experiments. I'll be presenting some of those next month at a conference. I'll start with kind of the biggest takeaway of what my data has shown so far, and that is that students are unsure. They are unsure what AI is. Their mental models are pretty mixed up. They're unsure how and when they are allowed to use it. And they're getting mixed messages all the time from parents, the news, their friends, and of course, different teachers with different ideas about AI. They are worried about their future, and all this uncertainty and worry is causing some inappropriate usage of the technology in ways that don't necessarily help genuine learning. Now, I know my visuals here are kind of hard to see, so I'm just going to talk it through. One thing I've found is that students right now are much more on the side of nervous and fearful about developments in AI than they are excited about it overall. Now, a minority of students here at BSU are using AI to cheat. It's about 2 out of 5 that admit using it in that way, some more often than others, like in ways that are explicitly banned or prohibited. But many more of our students are using it in ambiguous use cases. Basically, they're often not sure if what they're doing is allowed, so they do it anyway. Now, many of our students are using AI like all the time, like literally using Snapchat AI to do their homework. However, other students may be using AI without even realizing it. So they may have been told for a long time to use Grammarly to proofread their writing without realizing that Grammarly now uses AI to write entirely new text using the same LLM as ChatGPT. Now, meanwhile, the data out there is pretty clear that it is hard and going to be harder for us to detect the surreptitious use of AI, to catch the cheaters. As a signal detection problem, both us and automated detectors are imperfect. People who think they can catch all the AI probably are committing some form of toupee fallacy. You can find the obvious ones, you don't necessarily notice the ones you don't notice. And this is an area where false positives in that signal detection task can really damage trust. They can damage that student-faculty connection. And in fact, my data shows that first-generation students here at BSU are more likely to have been falsely accused of AI usage when they didn't use it to cheat. And this matches the same pattern that's been seen for English language learners being more likely to be falsely accused of using AI. Now, meanwhile, students tend to think that a lot of their peers are using it to cheat, but this is actually a pretty big overestimate relative to the number that actually do admit cheating with AI. And at the same time, there is a, we'll say, persistent view among students that out there in the real world, jobs and industry don't really care how you get your work done. Out there in the real world, they only care about the product, not the process, not how you got there. So things like plagiarism or using a banned AI tool to do things may not be a big deal in their view. And in fact, most of the students I surveyed did agree or strongly agree with this sentiment. And that agreement predicts them thinking that cheating with AI is morally acceptable, as well as predicting actual cheating with AI. Meanwhile, my data shows that our students all across BSU really want to learn more about AI because of what they're being told about the future and the workforce they'll be going into. But my data shows that most professors here are addressing it only shallowly, like in a syllabus statement. In fact, most of the students I've surveyed said none of their professors have integrated it into the class directly at all. So some, but very few of our students are getting direct educational experience with AI. So this is just a taste of some of the things I've been studying across a few different studies. But the takeaway here is that students are in this kind of worried and uncertain space right now. They're not totally sure what AI is exactly, when or how they can or should be using it. And yet they're told from many sources that they need to become facile users if they want to have any job in the future. So I think overall, our students are seeking more clear direction from us on how AI will fit into their education and into their future life and work. So yeah, thank you to eCampus for helping support some of this research, and I'm doing a bunch of other studies right now. I'm happy to answer any questions.
Awesome. Thank you so much, Dr. Stone. Audience, floor is yours.
Are there some positive use cases of AI being genuinely used in the classroom to support learning?
Yes, for sure. I think it's going like Pandora's box is open, right? It's here, and I think there are a lot of ways we can use it to genuinely make learning better. Some colleagues across campus have been talking about that at some other events. One example I like is it's really, really easy to create what's called a custom GPT, to create your own GPT right now through, like, for example, OpenAI's ChatGPT. If you have the subscription, you can make a custom GPT in like 5 minutes. And it can be something like, you can get creative with this, but one example might be creating a virtual TA for your class. If you have a large class to support, the virtual TA can be fed in your slides, your lectures on YouTube, your readings that you use in the class, and trained specifically on those. It's just kind of a wrapper on the general ChatGPT model. But then you can send a link to that to your students. You can even, give it a little branding and stuff. And then your students can inquire with this specialized GPT model that is specific to your class and ask questions. You can tell the GPT model when you're setting it up, you want it to not give them the answers, but to interact more Socratically with them. And then your students can use this as an extra source of learning support and potentially get a lot of benefits out of that. And it's very specific to your class. So they might ask about an example that was in your lectures, in your slides, or in the reading, and it can refer to that specifically and answer questions about that, which I think is really cool. And that's just one of many examples. Others are, of course, much more creative and can come up with even cooler stuff. Thanks for the question. Yeah.
Hi, just one last question. From my side, can you explain or contextualize a little bit more the particular result of 246, 92% not falsely accused for not first gen? Can you just elaborate on the result a little more compared to the other data?
Oh, yeah. So what's on the screen here? This is the students. I had a larger proportion of students who were first generation were falsely accused of using have reported being, so it's self-report, but self-reported being falsely accused of using AI in one of their classes so far. And that's just at a statistically higher rate than non-first gen students. So the 16% versus 8%.
Oh, it's in one of their classes. Okay, thank you.
Yeah. And so I did follow up, like how many times and then what was the outcome. So I don't have the results to present here. It's a lot longer, but I have some data on that as well. Yeah, great question.
All right, thank you.
Yeah, Ezra.
Do you see any sort of correlation, same with that chart, and maybe you don't have it off the top of your head, but like I almost imagine there'd be some correlation with like accusations in relation to student age. Do you see that at all?
Do you say student age? I have age. I haven't looked at that specifically for this question, so I could dive into that and email me if you want the answer to that. I could check it real quick. I haven't seen that yet, but it makes sense.
Thanks.
Wonderful. We're going to have to cut the questions here, but thank you again, Dr. Stone. We appreciate you coming and talking to us. All right, we will go ahead and move on to our next speaker, Dr. Richard Hutton. Dr. Richard Hutton enjoys a career as a conductor of university, secondary, community, church, and symphony choruses. He is the assistant professor of choral music education and an assistant director of choral activities at Boise State University. Dr. Hutton obtained advanced degrees with distinction in conducting from the University of Nevada, Reno, and Westminster Choir College. He is a national board certified teacher and a Yamaha 40 under 40 music educator. Dr. Hutton is on 2 committees surrounding artificial intelligence: the Boise State School of the Arts Storytelling and Technology AI Working Group, and the National Association for Music Educators AI Task Force, for whom he published an article in the national publication Teaching Music April edition entitled Artificial Intelligence at Your Baton, Leveraging AI in Choral Direction. He's going to talk to us today about music education in the age of AI. Dr. Hutton, the floor is yours.
Thank you, Catherine, and good afternoon, everyone. The image that I chose for this talk is one of my virtual choir performances during COVID. As a choral conductor, I never thought I would be utilizing technology to create virtual performance opportunities. And so I was quickly learning the skills of a video editor during that time, and it was a challenging time, but not something I want to revisit. But I chose this image to highlight how educators often rise to avail themselves of whatever is best for their students. And similarly, music educators are wanting to develop competencies with AI in ways that would be best for their students who are adopting them rapidly. Early in my engagement with AI, I learned that students were outpacing their teachers and utilizing AI tools in higher ed by 27%, with about half of college students regularly utilizing tools like ChatGPT. In the world of music education, when there are technological developments, take for instance, when the electric keyboard was being introduced, there's a fear that pianos are going to become obsolete. When we have developments in audio recording, there comes a fear that we'll no longer have live music performances. And we pay attention to these fears, just like Brian was mentioning, but we take them with a grain of salt as well. So I'm proud to be at an institution that doesn't balk at, but embraces innovation in an interdisciplinary way, like we're seeing here today. And I want to not only be utilizing these tools to see how my students can benefit, but also to see how my instruction can benefit. And I'm happy to hear in these talks excitement, but also caution and suspicion. So my area of research interest is in how educators, particularly choral music teachers, can be elevating their instructional practices with various AI tools, while considering how disruptive technologies raise concerns about bias, ethics, academic integrity, privacy, and more. So I want to give you just 3 quick examples that are practical with the time I have here of ways that other choral directors and educators in the Treasure Valley have integrated AI into our music education programs. The first area I'd like to highlight is assessment and reflection. So creating rubrics for formative and summative assessments can be super time consuming. I just want you to imagine the prompts, these prompts coming to life in seconds with AI. So create a 5-point rubric to assess a 7th grader's vocal performance of My Country 'Tis of Thee. or create a 5-question post-concert reflection assignment for my high school band's winter concert as we watch back the video of their performance. There are already platforms for music teachers to host lessons with AI tools that provide feedback and grade work. They can track the quality of practice time and hold students accountable. Musi.live is an example of this. As a choir teacher who had many weekly audio recordings submitted to me in an app called Sight Reading Factory that I would listen to individually and grade for accuracy. If there was some sort of AI plugin that would simply grade pitch and rhythm, this would be super, it would fast track my ability to discern the growth of students or where they're not demonstrating growth. So assessment and reflection concerning rehearsals and performance is a really important part of music education, and generative AI is a great resource in that regard. Choral music often involves singing vocal works in other languages that students are not familiar with. So word for word literal translations are most helpful for us, in addition to International Phonetic Alphabet or IPA transcriptions. So we know exactly what sounds to make when we're singing in those languages. And AI can help teachers and students quickly generate high quality translations and phonetic transcriptions to help them with diction. The treble voices of our two of our choirs here at Boise State are performing a piece in French this Sunday evening by the composer Poulenc. And the piece that we're performing doesn't have an IPA transcription in the standard resources that we have. So I created one with ChatGPT in seconds, and then I made my own corrections as I went through it, but it saved me a ton of time. So I do integrate it in a lot of ways in my own instruction. The music educator has many tasks related to marketing, visual design, communication with families, and preparing for and organizing all kinds of meetings and events, PLC meetings, parent-teacher conferences. We have plenty of administrative tasks that can be alleviated by AI. In healthcare, Abridge's technology records the conversations between doctor and patient during an appointment and pushes it to the electronic health records. I've read about that being utilized, and I can imagine it being utilized in music. Clinicians in healthcare industry, they go back and make edits. And so I think these technologies can be adopted in our music studios, our classrooms, our curricular ensembles, and in our departments. There are so many areas where education is being impacted by AI. We see standardized tests being graded by AI in Texas, and that actually is impacting the workforce. But I wanted to end quickly with a Bill Gates quote on AI in education. He says, "Even once the technology is perfected, learning will still depend on great relationships between students and teachers. It will enhance but never replace the work that students and teachers do together in the classroom." Thank you very much.
Wonderful. Thank you so much, Dr. Hutton. Audience, if you have any questions, now's the time.
That was great, Richard. And you talked a lot about the impact on teaching. I'm really curious on the impact on the creativity of music students. What are your thoughts on that, and how AI can play a role?
Yeah, that's a great question. I think in some cases, it could actually work to stifle creativity in some ways. But in many other cases, I think that it has great potential to bolster creativity. So in my own life, when I engage with AI, it sparks in me like a way to brainstorm like what's already going on and get the creative juices flowing. So I think with the various tools that exist to sort of engage creatively in music, there's sort of this hype curve of utilizing those tools and getting really excited about what they produce, but then it sort of peters out because it lacks the human element in a lot of ways. So, but I think of it as a support. There's a new app that just came out this week called Udio, and my colleagues and I have been playing around with it, and it sparked a lot of interesting rabbit trails of creativity, but then quickly loses its luster, like I mentioned. So I'm excited all those different ways that we can see students engaging with music in new ways, maybe evaluating AI music and seeing various ways that it stands up to our own creativity or ways that we think it fails. So yeah, great question.
Yeah, that's good. And I want to go back to what Brian presented, and are there ways students could cheat with AI in music?
Well, absolutely. I've had some cases of that sort of thing in my own practice. I think in the performing aspect of things, we're not there yet. Though there are some pretty convincing. I don't know if you have seen There I Ruined It or that YouTube channel. It's got a Johnny Cash song sung in the style of Johnny Cash. Sorry, it's an Aqua. I'm a Barbie Girl in a Barbie World song, but sung in the style of Johnny Cash with utilizing his so-called voice. And it's very passable. There are a lot of apps that are out now that are very, very human-like in the way that they sound in singing and even in choir and what I do. Where it's getting there. So in terms of passing muster with professors from students, I don't think we're there yet, but yeah, it could potentially be a concern. I think in academic integrity, we're dealing with that just like any other discipline.
Thank you.
Yeah.
All right, we'll go ahead and cut questions there. And thank you again, Dr. Hutton. That was wonderful. Our last speaker, unfortunately, has run into an issue. He was traveling today and he had a delay, and we were hoping that he was going to be able to make it, but it appears that he was not able to make it in. So what I'm going to do is I'm going to read his introduction, and then my hope is that we can have him record his presentation so that we can just splice it into this video, and then you guys will be able to see it on YouTube later. So we'll go ahead and move on to our last speaker, Dr. Michael Perlmutter. Dr. Michael Perlmutter is an assistant professor in the Department of Mathematics at Boise State University and an affiliate with the Computing PhD program. Dr. Perlmutter graduated from Purdue University with his doctoral degree in mathematics in 2016. His research is focused on subjects like geometric deep learning and phase retrieval problems arising in tychographic imaging. He also worked on problems related to applied probability, audio denoising, data set benchmarking, tensor compression, and has more recently begun working on problems related to remote sensing for ecological data, as well as data science for hydrology. And he's going to talk to us about AI and machine learning for data with geometric structure.
Hello, everyone. I'm going to be talking about AI and machine learning for data with geometric structure. So at a high level, the idea is that many successful machine learning algorithms are informed by the structure of the data sets. So for a few examples of what I mean by this is that for images and computer vision, many of the successful algorithms, such as convolutional neural networks, are designed to exploit the fact that the images of a pixel are arranged in a regular square-like grid. In a different line of work, for natural language processing, many of the successful algorithms exploit the fact that the words in a sentence appear in a sequential manner, one after another after another. My research is primarily focused on geometric deep learning, a new field which tries to take the success and extend it to fields where there's some structure, but it's a more irregular structure. So, for example, one of the primary interests of things I'm interested in is graphs. A graph is a mathematical object consisting of dots and lines between these dots. The dots are typically referred to as vertices or nodes, and they would represent the objects that you are interested in. And the lines are typically referred to as either links or edges, and they would refer to some connections between the objects. So one canonical example would be something like a social network, where each person could be a node, and the links would represent a friendship or other interactions between the people on the network. Another canonical example would be molecules, where the vertices could represent atoms and the edges could represent chemical bonds. The other main object of studying is a manifold, which is a low-dimensional object in a high-dimensional space. So here I've shown you a bunny, which is meant to be a two-dimensional surface in three-dimensional space. But what's also interesting is high-dimensional data sets with underlying low-dimensional structure. In particular, a lot of high-dimensional data sets, and here by dimension, I mean the number of pieces of information you have about each object of interest. The intrinsic dimension is very high, but there's a lower, simpler structure underneath. And we're trying to design algorithms that exploit this hidden low-dimensional structure, often by transforming the data into a graph by playing connect the dots in a principled manner. Some of the main theoretical questions are, how can we develop methods that capture the intrinsic structure of the data as opposed to superficial artifacts? So for instance, when you're trying to predict properties of a molecule, if you were to rotate the molecule in space, you don't change the underlying science. So you want to make sure that the answer of your algorithm is unchanged. And another interesting theoretical question is how much data is needed for analyzing high-dimensional data sets. Shifting in a bit of a more applied direction, we've recently done some work on modeling metabolic networks as a directed graph. And we've used techniques where we take this directed network and also some constraints informed by stoichiometry to predict the flux rates in the network. Alternatively, in an example in the manifold side of things, a lot of gene expression data has a superficially high dimension with a low dimensional intrinsic structure. And so we recently did some work where we looked at some gene expression data, and we visualized this in an interpretable way where the purple points are somehow more similar to each other than the green points and the yellow points and so forth. So in conclusion, I work in geometric deep learning, which aims to take the success of machine learning for data like audio, images, and text to data with a more complex geometric structure, such as graphs and manifolds. And some example applications are metabolic networks, gene expression, and predicting the chemical properties of molecules.
Thank you again, everyone, for coming and participating and asking questions. And thank you to our presenters for coming and presenting your research and your data. It was very, very interesting. And it's such a great topic to talk about, especially today, with the evolution of AI. So this ends the presentation portion of today's event.